Hello and welcome to this video for Chem 20 in the bonding units. This is the third lesson of the lessons that I have for bonding. In the last lesson, if you remember, we looked at drawing the Lewis structures and the structural diagrams for molecular compounds. We're going to continue looking at molecular compounds today and look at, in a 3D space, what shape these molecules would take on. So in this diagram here, it's actually showing us, I'm going to use a different color pen. Let's use purple. It's showing us, CH3, CH2OH, which simplified could also be written as C2H5OH. Okay? So it's showing again the atoms that are bonded, and the formula tells you exactly how many atoms of each element there are in that compound. So this is my carbon. It's bonded to 3 hydrogens, bonded to another carbon, which is bonded to 2 hydrogens, and it's bonded to an oxygen that is bonded to a hydrogen. Okay? So notice the shapes that are being taken around each what we call central atom. Carbon is a central atom because it's in the middle with multiple atoms around it. Carbon is also a central atom, and oxygen is a central atom. So there are 3 central atoms in this molecule, and they each take on a specified shape around them based on how many atoms are bonded to them, as well as if they have any lone pairs on them. And the oxygen in this case would have 2 lone pairs. Okay? So the shape around the oxygen is actually something called bent. And the shape around the 2 carbons is a shape called tetrahedral. So we're going to go through, there's 5 shapes that we talk about in Chem 20. We're going to go through and talk about those 5 shapes. And then again, how to know which shape you have and how to draw them on paper, because some of these shapes exist in 3D space. How do we show a 3D diagram on paper? So that's what we'll look at. So first of all, the reason, again, molecules are taking on these different shapes is because the electrons are repelling each other, okay? And so this follows something called the VSEPR theory, which stands for valence shell electron pair repulsion. So the electrons, again, in the valence shell are repulsing each other. And so the molecule adjusts so that these electrons are as far away from each other as possible. They want to pair up, and they will pair up multiple times in double and triple bonds, but beyond that, they want to stay apart from each other. The electron repulsion is greatest between lone pairs and the least between bonding pairs. So the bonding pairs can get a little closer where the lone pairs try to spread apart as far as possible. So as I mentioned, the shape is determined around the central atom. Now note that when you're looking at a molecule, so if I again look at something like CH4 as my simplest molecule here, the central atom is the carbon, and all the hydrogens are what we call terminal atoms. Okay, so my carbon is bonded here to 4 terminal atoms. So the terminal atoms are the ones at the end. Okay? Now, if you have a molecule that has only 2 atoms in it, whether it's 2 of the same or 2 different ones, there is no central atom. So make a note that molecules with only 2 atoms have no central atom. Now that doesn't mean they don't have a shape, okay? Their shape is actually quite simple. Whenever you have 2 atoms, their shape is always linear. Whether it's 2 atoms with a single, double, or triple bond, 2 of the same, 2 different, their shape is always linear. They're just side by side at each other. Okay, and that's actually the first shape that we're going to look at, linear. So if your molecule has only 2 atoms in it in total, okay, or the central atom has 2 terminal atoms around it, and there are 0 lone pairs around the central atom, the bond angles are 180 degrees, and the shape is what we call linear. Okay, so some examples. So HCl I already showed you. Those were when there was just two atoms in the molecule. Neither of them are central. They're both terminal. And again, like I said, whether this is a triple bond, a double bond, a single bond, the shape between two atoms is always linear when there's just two atoms. Okay, if you have three atoms though, and your central atom is bonded to two terminal atoms, there's no lone pairs around the carbon, the shape is going to be linear. So let's say right now you have all your structural diagrams drawn from your workbook homework. You're going to take the structural diagrams and convert them into shape diagrams, as well as give the shape name. So let's say right now you have the CO2 drawn like this. Okay, in a structural diagram, you can draw it however you want. There's no assigned shape that it needs to have. But when you're drawing it as a shape, you do need to put them at 180-degree angles apart from each other, so right across from each other. And again, the name of this shape would be linear. Okay? So again, these angles are 180 degrees. Now, you don't have to get out a protractor and measure it, but you're trying to spread the electrons apart as far as possible. So obviously, being on opposite ends of the carbon is spread out as far as possible. Okay, another example here is H bonded to C, that's triple bonded to an N. My central atom here is carbon. There's two terminal atoms. There's no lone pairs on the carbon, so again, everything spreads out at 180-degree angles. Okay? Now, it's also possible to have more than one central atom in your molecule. If there's more than one central atom, you do have to identify the shape around each central atom. So, for example, I can call this carbon 1 and carbon 2. They're both central atoms because they have multiple atoms surrounding them. So carbon 1, if I were to draw a ball to represent carbon 1, it's bonded to an H and bonded with a triple bond to a C, but that doesn't matter. Okay, so around carbon 1, it is linear. Carbon 2 is going to be the same thing. Carbon 2 is your central atom, the other one. It's bonded to a hydrogen and another carbon. Okay, so it is linear around each carbon. You draw it as one diagram, but you say that it's linear around each carbon. Okay, again, there's a triple bond in there, but that doesn't affect bond angles. It still is a linear bond. All right, the next shape we'll look at is tetrahedral. Tetrahedral is a 3D shape that we're going to draw. Okay, and I'll show you how to draw this 3D shape. So first of all, tetrahedral exists when your central atom has 4 terminal atoms and there are no lone pairs. The bond angles to spread out in 360 degrees equally would be 109.5. Methane is an example. So remember, my structural diagram is what we always need to start with. Now, obviously, to get the structural diagram, you may have to start with the Lewis diagram with the dots. Then convert it to a structural diagram, then convert it to a shape diagram. Okay, so I want to show methane, CH4, as a tetrahedral shape. Notice how, if this was my C, I have an H, this trying to show it 3D, I have an H going up and an H going off to the side that are in the plane of the page. But there is a C coming out at us, okay? So we need to show the bond getting bigger. And there's an H coming out at us, and there's another H going into the page. So we need to show that bond getting smaller, okay? So the shape you're going to draw is just like what I did there. You have an H on the top, an H off to the side. Going down on the bottom, getting bigger, is a triangle. So that's showing that the bond is coming out of the page. And then on another corner, going down, is a dotted backwards triangle where it starts with thicker lines and gets thinner, showing that the bond is going into the page. I don't like the look of this triangle. Let me try that again. Okay, now where do you need to draw the triangles? It doesn't really matter. Okay, I could instead draw it with the H here, an H here, this H going into the page, and this H coming out of the page, okay? The general shape, as you can see from this molecule, is the 3 H's at the bottom make like a tripod shape, so they should all be slightly bent down, and then the other H goes up, okay? One of the bonds comes out of the page, one of the bonds goes into the page. The other two are just normal lines because they're plain with the page. So it doesn't really matter, again, which bond goes where, but that's approximately the shape that you're trying to make, this tetrahedral shape, okay? Next, we'll look at pyramidal. Pyramidal is similar to tetrahedral in that it's another 3D shape where it looks very similar in that there's like this tripod at the bottom. There's an H that's plain with the page, an H that comes out of the page, which we draw with a triangle, and an H going into the page, which we draw with an inverted triangle, okay? And the reason this is happening is because there is this electron cloud, this lone pair of electrons that's pushing all of these bonds in that downward direction, okay? So when your central atom is bonded to 3 terminal atoms, like when you have ammonia, NH3, you're going to, again, this is your structural diagram, but your shape diagram needs to show that it's 3D and that, again, that it's making like a tripod shape. So my nitrogen with my lone pair, we can put a bond off to the side, a bond at the bottom coming out of the page, and a bond off to the other side but still going down to the bottom, inverted line, okay? That would be how you show pyramidal. Now notice the bond angles are a little smaller than the tetrahedral, which were 109.5, because this lone pair has more repulsion pushing those bonds down than the individual bonds were repelling themselves back in the tetrahedral shape. Okay, so that's pyramidal. Next, we'll look at bent. Bent sometimes is also called V-shaped, but what happens here is you have, for example, water. Your oxygen has 2 lone pairs, and it's bonded to 2 terminal atoms. These lone pairs are pushing the bonds away from each other so that it can't be a linear shape like another molecule with this central atom that has 2 terminal atoms, but the lone pairs, whether there's 1 or 2, bends those bonds in. So if this is how you drew water for your structural diagram, that would be fine for the structural diagram, but for the shape diagram, you need to show that it's bent, okay? So I usually put my lone pairs off to the corners, and on the corners going down, I put the hydrogens. Now notice how I'm not drawing any 3D lines here. That's because this is also a flat or planar molecule. It is in the plane of the paper. Nothing's coming out or going into the page if you just lay it flat, okay? The bond angles here are 104.5, so they're getting even closer to each other now as those lone pairs push apart. Another molecule that takes on this shape is nitrogen, that can form a double bond with an O and a single bond with an H. So my central atom, my nitrogen, is bonded to 2 terminal atoms, and there's 1 lone pair, but it still bends those bonds down rather than letting them stay apart at 180 degrees like carbon dioxide would when there's no lone pair. Okay? And then our final shape is trigonal planar. This is similar to pyramidal, where we have 3 terminal atoms around our central atom, but there are no lone pairs pushing those bonds down. So boron is actually an exception to our octet rule, where boron actually only has 6 electrons around it, okay? Because boron's in group 13, so it'll have 3 valence electrons, and so each hydrogen will pair up with one of their valence electrons, okay? There's no lone pair there. So in the structural diagram, where you might just draw it like this, okay, that's not what you want for the shape diagram. for the shape diagram, you have to spread them at 120-degree angles. So the shape diagram, what it would look like, I usually draw it one off to the side, one at the top corner, and one at the bottom corner, okay? Another example is CH2O. So there's a double bond to my O and two H's off to the corners. Now, a common molecule that you're going to see that a lot of students make a mistake with is, again, when there's multiple central atoms. Okay? So for my carbon 1 and carbon 2, carbon 1, if we look at carbon 1, it's there with a hydrogen, and another carbon. Okay? So that's carbon 1. So there's 3 atoms bonded to it and no lone pairs. So around carbon 1, it's trigonal planar. Carbon 2 is actually the same thing. It's bonded, the carbon is bonded to a hydrogen, another hydrogen, and double bonded to a carbon. Again, it doesn't matter if it's a double or single bond. That was kind of a funny little drawing there I did. But those are the 2 hydrogens and the other carbon that is bonded to. So it is actually trigonal planar around each carbon. Okay? Sometimes students will say it's bent around each carbon because they think there's only 2 things bonded here. If carbon, being my central atom, is also bonded to that carbon. So there's actually 3 things it's bonded to. Okay? Another common mistake they make is they just look at the overall center as one thing and think there's 4 terminal atoms, so they think it's tetrahedral. But that is incorrect. Okay? The correct answer is this molecule is trigonal planar around each C. Okay? The code around, sorry, we haven't talked about the code yet, but we'll talk about the code in a minute to help you remember. The code, the shape around each C is trigonal planar. Okay? Now, codes, that's what I was getting into. Oh, this is just a diagram that shows balloons would act like electron clouds, and they would try to spread out as far as possible. So if I were to tie them in the center, that would be my central atom. If I have 4 balloons around it, they actually take up that tetrahedral shape. If my central atom has 3 things bonded to it and no lone pairs, they'll make trigonal planar. And then if my central atom has 2 things bonded to it and no lone pairs, it'll make up a linear shape. So those shapes you could actually try with balloons and see how they actually make those 3D shapes, trying to spread apart as far as possible. Now there is a code system that we use to help us with the shape. Every different code corresponds to a shape. Okay, so again, the code is based on the central atom. So here nitrogen's my central atom, here carbon is my central atom. The next slide will show you what to do for elements or for molecules with only 2 atoms where there is no central atom. Okay, so the first number tells you how many terminal atoms are attached to the central atom, and the second number is how many lone pairs there are. So for NH3, I have 1, 2, 3 terminal atoms, that's my first number, and 1 lone pair. So the code is 3,1. Anytime you have a code of 3,1, that is a pyramidal shape. Okay? The next molecule has 1, 2, 3, 4 terminal atoms and no lone pairs around the carbon. So 4,0 is always tetrahedral. Okay? So the next slide here is going to show us the code systems and what they all represent. So we already looked at 4,0, which was tetrahedral. If you have 3,0, it's trigonal planar. If you have 3,1, it's pyramidal. If you have 2,2 or 1,2, they're both bent. I'll draw a little example of these. So I'm drawing a structural diagram right now, not a shape diagram. Okay, so there's my tetrahedral, which would be a code of 4,0. My CH2O, actually this one I'll draw as a shape diagram where it's all on the corners. NH3 has 3 terminal atoms and 1 lone pair. NO2 HNO has a lone pair, a double bond to an O, and a single bond to an H. So there's 2 terminal atoms and 1 lone pair. Whereas water has 2 lone pairs and 2 terminal atoms, giving us a code of 2,2. And then the last one is my linear molecule, where my code is 2,0. Like carbon dioxide. So there's 2 terminal atoms and no lone pairs. Now, here's that statement for molecules with only 2 atoms. There is no code for them, okay? So if I have HCl and I'm asked what the code is, you're going to say there's no code. However, the shape is linear, always, okay? Whenever there's 2 atoms, there's no code because there's no central atom. But the shape is always for them linear. Okay? And that is it for this lesson, looking at VSEPR theory and the 3D shapes that molecules take on. Thank you for watching this lesson.